for you in this? Stack it up, send it back.
This one is pretty.
So this is op 3 that I'm passing out.
It's on that pile. Yeah, it's on. Wait, where's the dumpling, Sam?
I left it in the fridge. She was so, actually no, she was so ungrateful.
We'll start with some questions. If you have anything from ops 1 or 2 or 6.1 or I don't know, something else. We'll start there. Does anybody have questions from any of those things? Op 1 or op 2 or 6.1 or some other homework? Anthony.
Can you go through number 5 on op 2?
The lifeguard one?
Yeah, that one.
Sure. Alright, so it says a lifeguard is stationed 100 meters inland from a straight shoreline. A swimmer is in distress 200 meters down the beach from the point on the shoreline closest to the lifeguard and 50 meters offshore. The lifeguard can run at a speed of 6 meters per second on sand and swim at a speed of 2 meters per second in the water. The lifeguard runs along the sand, enters the water at some point along the shoreline, and then swims directly to the swimmer. How far should the lifeguard run along the shoreline before entering the water in order to reach the swimmer as quickly as possible? Okay, well, let's imagine a picture here. So there's my shoreline. My lifeguard is somewhere here, and my swimmer somewhere over there, right? We're told that this distance is 100. The lifeguard's gonna go and run somewhere to the shoreline, and then swim somewhere to the swimmer. We're told that this is 200 and this is 50, right? Does everybody feel okay? And we're told that, basically what we're looking for is this point X, figuring out where he needs to enter the water so as to do this as quickly as possible, right? Because if somebody's drowning, you want to take your time to get in there. Does everybody feel okay there? So the question asks us to optimize what quantity? What are we trying to minimize or maximize?
Minimize the time taken.
Good, minimize our total time, right? So in this problem, we have some distances, right? The person's going to run, the lifeguard's going to run. We have some rates at which they can travel, right? We can run 6 meters per second and swim 2 meters per second. So our total time is just going to be like our run time plus our swim time, right? Everybody feel okay there? Now, the problem that I have with this is fine, it's a decent description of what's going on. That quantity time needs to be in terms of one variable. And what is the one variable that we're looking for in the question? It asks us to find the point that we're entering the water, basically that value for x, right? So I want to find a way to rewrite TR and SR in terms of that x. Is everybody okay with that plan? So I remember from like middle school science, that distance is equal to rate times time. Everybody's okay with that? So my distance running should equal 6 meters per second times my time running. Or that TR is equal to DR over 6. If I go to my picture, that would be like my DR, right? So let's call this side x then, and this side can be 200 minus x. I can use the Pythagorean theorem, or the distance formula, whichever you prefer, to write an expression for dr in terms of x, right? Everybody feel good there? Similarly, we can do the same thing for the swim. So if I go back and I look at my picture now, this is my distance swimming, is this diagonal. I can do the same kind of Pythagorean theorem again to get an expression in terms of x for that distance that we're swimming. So square root 200 minus x squared plus 50 squared. Everybody feel okay there? So now I'm going to use these two, and that's going to give me an expression for the total time that's in terms of one variable So that's kind of my first stage in modeling the equation, right? A picture of what I was trying to optimize. I wrote an equation for that quantity I wanted to optimize in terms of a single variable. Okay. Next thing I need to do is I need to look at the domain of this function. So what are the values for x that will be realistic? What's the smallest value that x could be? 0, right? If I think about the picture, what would x equals 0 mean? It would mean we did like this, right? Everybody's okay there? What is the biggest value that x could be? 200, right? And what that would look like then is like, we did that. Everybody agree? And those are both valid paths, right? Like I could certainly do that. So that tells me that my domain is closed interval. What does that mean for me later on? That I'm going to have to check the endpoints of that closed interval. Everybody so far so good? So now that I've determined the domain, I'm ready to proceed to the next step, which is going to be to find the critical points. So I'm going to need to find the derivative of t. So if I take the derivative of this, I can do it term by term, right? To take the derivative of the first piece, what do I need to use? A chain rule. So I'm going to pull the 1/6 to the front, and I'm going to have the derivative of the outside. Since it's a square root, I'd have, oops, let's do it this way, 1/2 times the inside to the negative 1/2 times the derivative of the inside, which would be 0 plus 2x, or just 2x. Is everybody okay with what I've written here? Now I'm going to take the derivative of the next piece. To do this, what am I going to have to use? Chain rules, plural, because I have 2 layers of composition, right? I have the square root, and then inside of the square root I have this quantity squared. So there's 2 chain rules that'll happen on this one. Everybody okay?
Would it be easier to factor that out?
You could FOIL it out and skip using a chain rule. The chain rule's not bad. It doesn't really matter. It's 6 and 1/2 dozen the other to me, but you could certainly do that if that's where you feel, if that feels simpler to you, no problem. You could do that, absolutely. Great question. Pretty good? So I'm going to have the 1/2, and then I'll have my chain rule, so derivative of the outside. Oops. Times the derivative of the inside. So the derivative of this is going to be another chain rule. So the outside times the derivative of the inside, and then plus 0, and then times the derivative of the inside Is everybody okay with what I did there? No. Zoom back out so you can see the whole thing. Now there's some cleanup I could do here. I'm not too worried about it at this stage though. So far so good? Okay. Now that I've taken the derivative, I'm going to look for the critical points. So I look at where the derivative is 0 and where the derivative fails to exist. Are there any values for x that make this undefined? None that are outside of the domain anyway, right? I can't get a negative number underneath the square roots because I just have positive plus positives. I can't get a 0 denominator because I have, non-zero plus non-zero, or positive non-zero plus positive non-zero, because I have the negative exponent now, so I do have to be mindful of that, but can't happen here, so I'm good to begin or continue, right? This is none. Do you think I'm going to try to solve this thing equal to 0 by hand? What am I going to do? I'm going to use my calculator. How am I going to use my calculator to solve that? I'm going to graph it and look for the 0, right? And in fact, I'm not even going to type this in. I'm going to type in my original into y1. In y2, I'm going to tell the calculator to give me the graph of the derivative, and then I'm going to look at the 0 for that. I'm not even going to type this in because Lord knows I'd probably make a mess of typing it in, right? Do we need to review how to do this on the calculator? Are you guys okay? It's okay? All right. So when I do that, I got to look up what this number was again. There it is. So I got about 184.67. And again, those are going to be meters. It's the only critical point inside the domain from 0 to 200. Okay? Do I know that's a maximum, or do I know that's where the maximum or minimum time occurs at? Don't, because what else do I have to check? The endpoints. Again, I'm just typing this into my calculator. There's no way I'm doing this by hand. So those were the outputs from my calculator. So that's my minimum time. Takes me 61.15 seconds when I enter the water 184.67 meters down the shoreline or whatever. So I want to run almost the entire way, almost as far as I can before getting in the water. But the actual optimum, the shortest time, is the time, right? So I'm looking for the 61.15. Oh, I guess the question asks how far, so I want the 184.67. Excuse me, depends on kind of how they ask, right? What do you guys think? Again, the hardest part of this problem should have been the initial setup, right? Once you have an equation in terms of a single variable, we analyze the domain, find the derivative, solve for the critical points, and then check for which one is the maximum or minimum, depending if it's open or closed. And that's the gist of it. So like the cleanup at the end, once you've gotten the thing modeled, should be relatively easy, right? You guys will see in Opt 3 that I handed out to you. The main difference between like Opt 2 and Opt 3 is just that the answers in Opt 3, there's basically no numbers. Everything is like a non-numeric coefficient. So you can get answers like 4R or, you know, like L divided by 7 or something. Like you're going to get letters in your answers. This will be like, this is my plan as my last set to give you guys. They're basically the same thing, but now you have to do things. You can't use your calculator to do the solving, like you have to do it by hand because it's all letters. So you have to algebra it. You can't like get away with the calculator in it. But most of the situations are basically the same as like the Opt 1 situation, so it shouldn't be too bad. You guys feel reasonably better about at least this one in particular? The process in general, again, basically model the situation in terms of a single variable. Look at the domain, decide if the interval you're solving over is open or closed or one-sided closed or, you know, find the critical points and then determine if they're mins or maxes depending on whether the interval is open or closed. Is that okay? Today, we're going to start talking about 6.2, and we're going to talk about calculating volumes for figures. And this lesson we're about to do of calculating volumes, this covers two sections in our textbook, 6.1 or 6.2 and 6.3. I'll probably take at least 3 class periods doing this. There's kind of 4 different techniques that we're going to look at. We'll look at 2 techniques today, 2 techniques next time, and then kind of like plug this stuff all together and take a day of just talking about like how do I choose the right technique to use for a given problem. What am I looking at? How do I set this up after I've selected the technique? So we're going to work from, you know, like the individual techniques where the selection shouldn't be a problem. Worry about how to do that once you've identified the technique, and then we'll take a day of just like selecting the technique. Sound good? So the first thing we want to start with is just taking all the way back to geometry and talking about calculating the figure or calculating the volume of like a cylinder. So if you have like your canonical circular cylinder, to calculate the area or the volume of this cylinder, I need the area of the base times the height, right? Since the circle is the base, it's just pi r squared times the height. A box is technically like a cylinder because the box, the base of the box and the top of the box are still the same. And any cross section I take in between those bases is the same shape. That's kind of our more advanced definition of a cylinder. Is everybody okay there? Or even something like this, where the base is this weird, like, parabolic shape. Still just like a cylinder, area of the base times the height, since every cross section we take parallel to the bases is the same area as the base. Everybody's okay? But what if we have like some cuckoo crazy irregularly shaped object? Now, this is kind of like a cylinder in that I have like two bases that are parallel to each other. Those bases may not be the same size, and certainly the cross sections, as I'm cutting in between the parallel bases, are not the same area. What am I going to do here? Well, the idea is, if I just take some slice, some arbitrarily thin slice, I can calculate the volume of that slice by calculating the area times the width. As long as I'm slicing it really thinly, the difference in like the size of the top base and the bottom base are basically the same, as long as I'm slicing really thin. And I'm going to calculate the volume for that little tiny thin cylinder that's now like a cylinder. And I'm going to do that for every single slice on there. I'm going to add up all those volumes, and that should give me the total volume for the figure, right? What does that process sound like? But yeah, like a Riemann sum, or really integration, right? If we slice them infinitely thin, we're talking about really just doing integration. That's going to be the idea. So this first method that we're going to talk about is, or these first two methods, are going to be based on like taking slices and calculating the volume of these little tiny slices and adding up infinitely many slices, and basically we're doing an integral. Okay with that? So if my slice here has area A of x, it's going to have width like dx. So the volume of that slice is going to be like A of x times dx. Everybody's okay with that? I'm going to add that up for all possible cross-sectional areas. And that just becomes a integral from a to b of A of x dx. So a general formula for the cross-sectional area times that dx. Is everybody okay with that idea? Let's start putting this into practice now, okay? So here we're asked to show the volume of a sphere with radius r is 4/3 pi r cubed. Everybody's okay? That's what we're trying to show. So here's a picture of a sphere. I'm going to think about taking my cross-sectional slices along the x-axis. Everybody's okay with that? So in this case, my cross-sectional area is going to depend on x. So when I'm integrating, I'm going to be integrating with respect to x. Is everybody okay there? If I'm slicing along the x-axis, I'm going to begin my slicing at the x-coordinate, negative r. And I'm going to slice all the way until I get to the x-coordinate, positive r. So those are going to be the bounds of integration for me. Is everybody okay there? Okay. So now let's look at this cross-sectional area. So my cross-section there is a circle, right? I know the area of a circle is pi r squared, but the radius in this case I need to write as a function of x, because at each different cross-section, the area, or that radius is going to be a different length, depending on the x that I pick. Is everybody okay with that? So if I look at this arbitrary cross-section that I've drawn, this point here is like an x comma y, right? The radius of my cross-section is represented by the y-coordinate. I need to find a way to rewrite that y-coordinate now as a function of x. You okay there? Notice that I have a right triangle with base x, height y, and radius r. So we know that x squared plus y squared is equal to r squared. I'm now going to just solve this for y. Notice that I dropped the plus or minus when I took the square root of both sides. Why was I able to do that? So radius, it's a length of a shape. That should be a positive number. So that's what y is equal to. So that's going to be my function for r. Does everybody feel good there? And I know the square is going to cancel the square root. So that's the integral that I'm going to be solving. Is everybody okay with the setup there? Again, I'm just using the formula, integral from a to b, cross-sectional area dx. And I did pi r squared because the shape of my cross-section, if I'm cutting a sphere, is going to be a circle, right? Is everybody able to imagine this in their mind? This three-dimensional imagination is a really useful skill for this topic. If you're not good at that while you're working on the homework, like pause and take a minute and try to imagine the shapes that you're looking at in your head. Think about what the cross-sections are going to look like in your head. It really helps your intuition about like what you're doing and why you're doing it and how you're doing it, if you're able to have enough imagination to see these things. Now, I don't expect for you to have that imagination right now, because it's the first time you're doing this. Some people, this is going to come very easy to. Some people have a devil of a time with the imagination piece. But you should work on building that skill out, in particular if calculus is a subject that you're going to be spending a lot of time with future engineers. Okay. I'm going to now do the antiderivative here. I'll pull the pi out front. What's the antiderivative of r squared with respect to x?
R to the third over 3.
No. That would be if you were integrating with respect to r.
Oh.
Is r a variable here? No. R is a constant. So what is the antiderivative of r squared going to be? R squared x. Right, what's the antiderivative of 2? 2x. What's the antiderivative of constant? Cx. What's the antiderivative of r squared? R squared x. Everybody okay? And then the antiderivative of x squared now, Frankie, that's x cubed over 3.
That's what you're looking for.
Yeah.
That's what you, yeah, definitely.
Frankie, that's the same answer second hour gave me, was that same thing, so don't feel, it's what I expected, that's why I asked, because it gives me a chance to like help clarify what it is we're talking about. Because it's hard, right? Like you think R, that's a variable, anti-direct, it's like not with respect to the integral though.
Okay.
Okay. Everybody good to hear? Let's start plugging them in. Everybody's okay with me plugging in? I'm going to distribute through the negative. Good there? So I have r cubed minus r cubed over 3 minus a negative, so that'll be plus r cubed. And then negative r cubed is negative, so I'll just have minus r cubed over 3. We still have the pi out front. So r cubed minus r cubed over 3 is 2r cubed over 3. And then I have another 2r cubed over 3, so I have a 4r cubed over 3. There we go. We're done. Shocking. It's what we knew the volume of a sphere already. So far, so good? The rest of this lesson, we're just going to continue looking at more examples of kind of doing this process. Help build some intuition. The functions that we're going to move away from just the three-dimensional figure. We're going to start giving you guys a function and describing how we're going to build the three-dimensional figure from the function. To start, I'm going to give you the graph of the function and the graph of the three-dimensional figure. Eventually start peeling away some of the givens as you start building out your own intuition. Eventually it'll turn into just getting the words and no pictures at all, but we're going to start with the pictures so that we can start building some intuition. So this example says, find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals the square root of x from 0 to 1. Okay, so this is the graph of y equals the square root of x. And we're talking about the area under the curve from 0 to 1, so it's the blue shaded region here. Is everybody okay with that? We're then going to rotate that region about the x-axis. So we get a shape like this half, like this dome shape. All dome on its side. Is everybody okay there? Now, to calculate the volume, I'm going to imagine my slicing is going to be happening perpendicular to the volume of rotation. So I'm going to slice along the x-axis, which means that I'm going to be integrating with respect to x. Is everybody okay with that idea? I'm going to begin my slicing at 0 and end my slices at 1. Everybody okay with the initial setup here? The last piece I need then is an expression for this cross-sectional area based on x. So if I look at the cross-section I've drawn in here, the radius is going to go from the x-axis up to our function, right? So this line here is r. This point here would be x comma y. So my radius is going to be the same as the y coordinate on that point. Everybody agree with that? Because this curve is y equals the square root of x, y is the same as the square root of x. So that radius is the square root of x. Is everybody okay with how I resolve that? Follow the logic, the geometry that happened here. It's a very visual topic. If you're not able to draw the pictures and draw in where the things are and use the coordinates to justify what your radius is and all this, it becomes very overwhelming very quickly. If you have a good sense of like how the function and the graph and the coordinates all relate together, this usually goes pretty well. So my area function is going to be pi r of x squared. And we have that our r is square root x. So this is just going to be pi x. Is okay? Now it's time to integrate. The integral of, or the antiderivative of x is x squared over 2. And then I just plug in. And pi over 2 is my volume. Does everybody feel okay on that? So again, the formula that I'm using here is integral of cross-sectional area dx. Now, this method that we're doing is called the disk method because these slices look like a disk, like a coin, like a CD. I don't use CDs anymore. Coins. Still used a coin before. I know nobody carries them anymore. Maybe if you go to the vending machines regularly. You probably still pay with your credit card though. Everybody's okay? Let's do another. Okay. Find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So again, we have y equals 8, x equals 0, and then my curve y equals x cubed. So we're talking about, this is our shaded region, and we're rotating this time about the y-axis. Everybody's okay there? Okay. Now typically, I'm going to erase all that. The goal here is going to be to slice perpendicular to the axis of rotation. Since we rotated about the y-axis, I'm going to be slicing horizontally this time. Everybody's okay with that? Since I'm slicing horizontally, the slices depend on which coordinate? The y coordinate. So our integral is going to be with respect to y. And we're going to begin our slicing at 0 and end our slicing at 8. Is everybody so far so good? So this is what our three-dimensional picture looks like. I'm basically rotating this around the y-axis. I'm going to get like the top of a champagne flute, right? Is that kind of what that shape looks like to me? Except it's solid all the way through instead of having being a calc. Everybody's okay? If I take my cross-sectional area, it should be easy to see that what I'm going to have is a circle. But this time, these circles are dependent on y. So if I draw in that inner radius, it's going to go from like here to here, right? So if that's the point on the curve, that's an x comma y. This distance is my radius, which is an x coordinate, because we're talking about over. Everybody's okay there? But I need to rewrite this x in terms of y. Since this point is on the curve, y equals the square, or y equals x cubed. Oh, come on now, stop. I could take the cube root of both sides. And think about this as then the cube root of y, comma y. Which means that my radius is the cube root of y. So my area function would be pi times y to the 2/3. Does that feel okay? Don't look so defeated, guys. If this is a problem, you need to stop me and say something, and I'd be happy to elaborate and do more detail or talk through how I knew to do something or what I did to do that, or I'll look very beaten down. Sorry, it's been a rough week, I know. So far, so good. Okay. Now we just do evaluate our integral. So I'll pull the pi out. The antiderivative of y to the 2/3 is oops. That's an 8. Well, good. So we evaluate. Since the denominator of this exponent is a 3, that's the same thing as a cube root. The cube root of 8 is 2. 2 to the 5th is 32. Times 3 is 96 over 5. And then minus 0 is, 0. So far, so good. Now, all of these all these three-dimensional figures we've looked at so far are convex, right? They have no holes, they have no indents, nothing, right? If I pick some point on the surface and draw a line through the center or through the figure, there's no way that that line can come outside the figure and then go back inside the figure, right? That's what it means to be convex. What are we going to do if it's not convex? What if we get a concave shape? Let's look at this next example. So here we have the region R is enclosed by the curves y equals x and y equals x squared, and we're rotating about the x-axis. So notice here, there's going to be some empty space, right? When I rotate this around the x-axis, this area in green is going to be empty in the three-dimensional figure. You guys picture that? It's going to kind of look like a distorted funnel, but it has no opening at the bottom. Kind of see it? Very important that you're able to imagine these things in your mind's eye. It makes a big heaping difference. I'm going to erase this. So this is the book's example. I don't particularly think it's very good. So I'm kind of looking at something like that in my mind's eye. You kind of see it? So when I take my cross sections as I go through, they're going to have like an opening in the middle. You guys see that? This method that we're going to develop right now is called the washer method, because this shape looks like a washer, not like a washing machine or a dishwasher, but like that piece of metal hardware that you put like the screw through and then you screw down to protect the surface you're screwing into, because it's a disc with a hole in the middle. Everybody's okay with that? So my area function, ignore these things, I'm going to have the outer radius, so I'm going to calculate the circle with the outer radius, and I'm going to subtract from it the circle inside, right? Is everybody okay with that idea? Okay. Let's erase some of this stuff. So, I'm going to use this picture because it's a little bit easier to see the radius on. So if I pick some arbitrary spot on the axis of rotation, that's where my radius is going to originate from, right? Here we're told the axis of rotation was the x-axis. My inner radius is going to go to that inside function. Is everybody okay with that idea? That point is an xy, so the inner radius is the same as which coordinate? The x or the y? The y, because it's a vertical distance, right? Now, I need this radius in terms of x. So if I look at the curve that we're on the curve y equals x squared. So my inner radius is x squared. So my inner area is going to be pi x squared squared. Does everybody feel okay? I'm going to erase this work because it's just going to get too busy and do the same thing now for the outer. Everybody's okay? Oh, I was having so many problems with this second hour. I can't believe it's doing it to me again. It's frustrating, guys. Don't need you to send any reports to Microsoft. Nope, I don't need you to recover anything. There's nothing to recover. Try it again. All right. So we had said that we had gotten that far. Now we're going to do the same thing with the outer. So again, I'm going to just pick like an arbitrary point on my axis of rotation. And this time I'm drawing to the outer function. Everybody okay with what I mean by inner and outer? Okay. So that point is an xy also. Which coordinate is going to represent the stop? Don't glitch. really upset today, guys. No. It's been a frustrating day. Okay. Which coordinate is the same as R? Y. But I need to rewrite this in terms of which variable? X. This is the function, or it's on the function y equals x. So my R outer is just x. Everybody okay there? So my volume then is going to be the integral. We're integrating perpendicular down the axis of rotation still. So we start at x equals 0. We end at x equals 1. Because we're going down the x-axis, it's with respect to x. And then we have R outer minus R inner. Everybody's okay there? And now we just evaluate. So I'll pull the pi out, antiderivatives. So 5/15 minus 3/15 is 2 pi over 15. Notice I just wrote minus 0 for the subtraction. So 0 cubed over 3 minus 0 to the 5th over 5 is just 0. So I just save myself some writing. Okay. Let's do another. Okay. Now, what if we start rotating about things other than the x and y axes? What if I use other vertical or horizontal lines as my axis of rotation? So here, this is the same two functions we just looked at, y equals x squared and y equals x. But this time we're going to rotate about the line y equals 2. So we're still talking about this same region here, but now we're going to be rotating about this line. What is this shape going to look like? Well, this piece is going to spin around, so I'm going to have like just
Good luck with it.
yeah, it's been a really fun day. So let's try this again. So I'm about 1 unit up. So it's going to create a opening there, right? And because there's a gap between the function and the axis of rotation, I know it's going to be like a straight hole through this. And we have a gap of about 2 units from the figure to the axis of rotation. So my second opening is going to look like this. Now it's a straight line as my inner function, but I have like a curved line for my outer. So it's kind of like a funnel, but not a normal funnel, like a kooky funnel, because it's not the same thickness all the way through. It's thicker in the middle than it is at the ends. You guys visualize that there in your heads a little bit. Again, once you have the feel for it, the three-dimensional picture doesn't matter that much, but like initially, early on, it really helps to be able to visualize what it is you're trying to find the volume of, because identifying whether you should be using a disc or a washer or some of the other methods that we'll look at later on, that really helps. And then to be able to figure out what the inner and outer radiuses are and all that stuff really makes a big difference if you're able to visualize this. I'm going to erase this picture now because I have only one thing to work from, and we'll get too busy if I try to leave all this stuff on here.
Sorry, can you say one more time how you figured out that shape?
So yeah, I'm looking at the axis of rotation, right? So I have like from there is going to be like the center of a circle. So it should extend like 1 unit down, so it should match 1 unit up. So that's like my circle. Here I have like, again, the center of my circle, so I've gone like 2 units down. So it should extend like 2 units up. The inner function was this straight line. So that should be the inner edge of my funnel. And then the outer function is like this curve. So it's going to be like a fat guy. And because there's like a gap here in between the function and the axis of rotation, I know that these like openings, it's like an opening through the middle now.
Okay.
Does that feel okay?
Yeah.
Again, it's one of those like, once you've done a couple of these, like it gets easy to visualize it, but I acknowledge in the beginning it's quite difficult. All right. So again, we're going to be slicing perpendicular to the axis of rotation. We're rotating about a horizontal line, so we're taking vertical slices, which means we're incrementing down the x-axis. So we're going to be integrating with respect to x. We begin our integration at x equals 0 and end our intersection, or end our integration at the other intersection, which is x equals 1. And now I know that this is going to be, I need to calculate an A outer and an A inner because this is going to clearly be a convex figure because there's going to be a hole through the middle. So let's start with a arbitrary for A outer, I suppose. So I'm going to start with the axis of rotation because that's where my radius is going to begin. And it'll extend to the outer function. Everybody okay there? Now this is the point xy, right? On that function. So this distance down here is y, right? And this whole piece here was the distance from 0 to 2. So that's 2. So our outer should be 2 minus y. Is everybody okay there? Now, we want this in terms of x because we're integrating with respect to x. So this point is on the curve y equals x squared. So the y there is just x, or it's just x squared. So my r outer is pi 2 minus x squared squared. Is everybody okay with what I've done there? I'm going to erase this in a moment because I now have to do the same thing for the inner and it just gets too crowded on the OneNote to do it at the same place. Is that okay? So I'm going to erase. So again, just going to pick an arbitrary spot on the axis of rotation. This time I'm drawing to the inner. So that's like my inner function. This is some point x, y. So this distance must be the same as the y coordinate. This distance from here to here is still 2. Oops. Everybody's good? So what is my r inner going to be? Again, 2 minus y. But this time we're on the line y equals x. So that means that this is really 2 minus x. Does everybody feel okay still? So that's going to be my integral. Is everybody okay with what I've done? These ones are a bit more challenging to figure out the expression for the radius. You really got to be able to draw the picture. And I think the easiest place to draw the picture is in the two-dimensional graph rather than in a three-dimensional graph. To do the antiderivative of this, I don't have a way to do this antiderivative as it's currently written because it would require a u substitution, but I won't have a extra negative 2x anywhere. So rather than try to muck around and do something complicated, I'm just going to FOIL this thing out. And as long as I'm foiling the one out, I'm going to FOIL the other out. And I distributed the negative through that second FOIL also. Does that feel good with everybody? Anthony, here's a case where the foiling made a heck of a lot more sense than trying to go and make this a harder integration problem. 4 and negative 4 cancel out. I'm going to combine the other like terms. I have x to the 4th minus 5x squared plus 4x dx. And now I can do my antiderivative. I have 1 to the 5th over 5 minus 5 times 1 cubed over 3 plus 2 times 1 squared, and then just minus 0. And that's bigger than 1. I'm not going to bother grinding the, or bigger than 0. I'm not going to bother grinding out the arithmetic there, because quite frankly, my brain is kind of feeling a little on the crispy side, and I just don't want to make the math it right now. Is everybody okay? Leave some fraction arithmetic for you guys. Same setup, but this time we're going to rotate about a vertical axis, x equals negative 1. So this time we're like rotating about that guy. So if I imagine what this is going to look like, kind of the same shape, but this time it's opening up instead of opening to the side. That feel okay with everybody? So as I chop, I need to chop perpendicular to the axis of rotation. I'm going to be chopping along the y-axis. So I know I'm going to be integrating with respect to y. The y-coordinate goes from the first intersection in 0, 0. To the second intersection, 1, 1, so we're integrating 0 on the y, 0 on the 1, or 1 on the y. Is good? Okay. And again, we obviously have a washer situation here, right? You guys can see that? So again, I'm going to just draw my picture here. So I'm going to draw my arbitrary radius for the outer circle. It's going to start from the axis of rotation. And go to the outer function. Everybody's okay? Now I know this distance is 1 from x equals 0 to x equals 1. This distance is x, right? Because we've gone x over to get to that point. So our outer must be 1 plus x. Everybody's good with that construction? Note, though, that I'm integrating with respect to y, so I have to rewrite this x in terms of y's. Now this x is on the curve y equals x squared. So x is just going to be the square root of y. So my outer area is going to be pi times 1 plus, square root y squared. Okay. Does everybody feel okay to this point? I'm going to erase all this now and do the same thing with the inner function because, again, it gets too busy to have all this stuff on there and it gets confusing. I'd love to leave it all up, but my picture isn't really big enough. So again, I'm going to pick an arbitrary point on the axis of rotation and draw it to my inner function. That's my R inner. That distance is still y. That point is x comma x, so that's an x. So my R inner is 1 plus x. But I need to be integrating with respect to y, so I have to rewrite this in terms of y. Since we're on the line y equals x, I know that, x is equal to y. That can just be 1 plus y. And it's integration time. Again, I don't have a good antiderivative formula for these guys. This is what they're currently written. What am I going to do? Boil them out. So I have 1 plus 2y to the 1/2 plus y minus 1 minus 2y minus y squared. 2y those guys cancel out. So we have 2y to the 1/2 minus y squared. And so we do our antiderivatives. 2 times y to the 3/2. Let's say 2/3 y to the 3/2 minus y squared over 2 minus y cubed over 3 from 0 to 1. So I have pi times 4/3, 1 to the 3/2 minus 1 squared over 1 minus 1 cubed over 3 minus 0. And 4/3 minus 1/3 is 1 minus, so I have pi over 2. There we go. That was a workout. I'm going to skip this last couple of questions because that's kind of a different problem method that I don't want to get into today with just a few minutes left. The homework assignment from this should be 1 through 17 odd and 31 to 33 odds. We'll make this due the last Sunday of break, so not this Sunday, but the following Sunday, so not a big rush to get to it. Please, while you're doing this homework assignment, do the integrals by hand. I've been working through grading your tests, and it's been a bit of a mixed bag on your ability to integrate something by hand. So many of us could use a little bit more practice on that. I would encourage you to do these both problems, the integration by hand, and not use your calculator. I think it would be excellent additional practice and go a long way to like building that skill to a better, to a higher level. I will not be here on the 23rd, the day you guys come back. I'm gonna leave for you guys a delta math based on this lesson to work on in class. On that delta math assignment, you'd be free to use your graphing calculator to compute the integral in an effort to like not make it take a million years. But that'll be what you'll work on that day while I'm gone. So opt 3 and this guy are the final Sunday of break, not this Sunday, but the following Sunday. You'll have a delta math that day you come back. I won't be here for that. On that following Wednesday, we'll look at this, talk about the opt homeworks, maybe figure out a day to do the opt mini thing, and then continue on looking at the other 2 techniques to compute these volumes of figures, because there's 2 other situations that we want to talk about. Basically does it for me. What do you guys think? Is that okay? All right. I'm going to stop here. Everybody's going over, everything's okay in general? You made it, one more day, and it's some time off to recover a little bit. I think basically after we come back, it's like 6.5 weeks of school or something when we come back from vacation before you guys are done for good. I think something like that. Between 6 and 7 weeks of classes, right? I know. You still have another week off for spring break coming. We have some days off in Irish week and stuff, and there's some conference days. You know, February's basically, you have a week left, and less than a week left in February. Then we're into March. You guys are done usually that first week in May. Something like that. There's not that many days left, guys.